I am happy to be here. My name is Vladimir Vivien, and today we're going to talk about generic programming. And before I get started, let me switch my screen. All right, so you should be seeing my screen. Again, we're going to talk about generic programming in Go. And once again, my name is Vladimir Vivien. I am a software engineer and also a book author. I have published a book on Go back in probably 4 years ago. And I also enjoy writing about tech. And like I said, today we're going to talk about the generic proposal that has been released back in June 2020 for Go. And it's a long document, and it's a very thorough document. And what we're going to do in this presentation is take a super high level view and look at some example at the end to make sure that what I'm talking about makes sense. Parametric polymorphism in Go, I thought we were talking about generics. We are. So before we jumped into what generics are and how they're being proposed for Go, I wanted to take a step back and talk about what exactly we mean by generics. And parametric polymorphism is a way to write code correctly without having concrete types. And to the astute listener or watcher or viewer of this session, you may be like, hey, I thought we were able to do that in Go anyway. And you would be absolutely correct. There is, since Go's inception, there's always been a way to write correct code without concrete type, or at least known concrete type at build time. And we'll see, we'll look at examples at how that's being done today and compare that to what's being proposed as far as generic. So for parametric polymorphism, the way it is being proposed to be done in Go is with type parameters used to define generic functions, generics, and generic types. So now that we know what we mean by generics and what we need by type generics and generic functions, let's see how that would work in Go. One of the first proposal is generic types on a function. When you define a function, you can not only define type parameters as we do today, regular parameters as you do today, but you can also add type parameters. And we see that being done, we see that being done with the first set of parentheses with the type keyword. We're proposing that type T for this particular function, type T is a type parameter that is being added to the function or defined in the function, and then followed by the regular non-type parameters that also are defined to use type T. And we also see that function as defined can also return type T. Now, at this point, we know nothing about what type T is. We don't know when someone uses our function what type T will be. But as we continue, we'll see that the proposal has a mechanism to allow you to narrow down or filter down types so that we're not back in a scenario where we're using something like an empty interface. So we'll see how that's done. And this is how you would use the type parameter. Here we're using the function f, and the first set of parameter that was defined as a type parameter. Here we're instantiating it as being an int, and we see that param now can use that type parameter as an int, and function f itself is returning an int. So now this is what using a generic function would look like. And this is, I'm highlighting where the parameters and the types are placed. Not only functions can receive type parameters, but types can also receive type parameters. And here we see type chan being defined as having a type parameter. So type chan takes a type parameter t, and t is used as the underlying type for type chan. So let's see how that's used. Similarly to what we saw with the function, with the generic functions, here we're seeing now the generic function is using a generic type. Chan does not mean anything by itself, so you have to instantiate Chan with a concrete type, and that's what we're doing here with int. Now the compiler will know what you mean by Chan and what the underlying type to be used with a channel would be. Constraints on type parameters. Now, if parameters, if we didn't have a way to specify certain constraint on parameters, we would run in trouble really quick, because when we're writing out generic functions, we have no idea what could be in a type. One way to do that is to use what we call constraints, and constraints are implemented with interfaces. And if you've been following, the whole generics in Go, you probably know that constraint used to be called contracts. And with this new proposal, it's been basically simplified to use things that were already in Go, and interfaces were already in Go, so now we're using interfaces. An interface allows us to specify a set of behaviors by means of methods that our type, that the type parameters that we pass in our functions can have. So now when a type is said to be a type parameter, if it doesn't meet that constraint, the compiler will know right away it is not the right type. So let's take a look. Here, this is the new function f. We were defining it with a type parameter t, and this time t takes the constraint that we saw earlier. And now when t is used and we use f, whatever type we specify as a type parameter for f, when we instantiate it, it has to implement string. Another feature that has been introduced in this particular proposal is what we're calling a type list. There are certain types, especially the basic types that are in Go. They support operators. They support certain built-in functions that you have to have a way to specify those functions and those built-in functions and those operators. One way we could do that is, if a type coming in, we could list a list of supported types in our constraints, and when those types are coming in and being used by a function, for instance, we know that we can apply certain built-ins, like for instance in string, we could apply the length or len function or len function in bytes. But if it was an integer, we can't do that. If the type that we push in is an integer, we can't do that. But the constraints allow us to filter out and to craft the attributes about the type very precisely, so that when we get ready to specify the type that we want to use, the compiler knows exactly what we mean. And in the demo, we'll see how this is being used. I put that up there because some of the examples that you will run into are use square brackets instead of parentheses, like I've been doing. Here we see that function f uses the square bracket to specify the type parameter t, and when it is being used, function f also uses the square bracket to specify the instantiated type of int. Now, I think at this point, the Go team has not settled on which format they're going to choose, and I'm pretty sure they're looking for feedback. Personally, I'm on the fence. I think I sort of like, for some reason, I like the parentheses, but I think the square bracket could work as well. And like I said, the proposal is online. This is the blog that introduced the proposal, and that when it was released, the URL for the proposal itself is super long, so I just put the blog up here. Once you visit that blog, it'll walk you through some of what's being introduced in the proposal and how you can play with tools that allow you to build your code, which is what I'll be using in the demo, to test out generics in Go. A lot of talking. Let's get to the demo. I'm going to switch to my IDE so we can continue. So what we're doing here, let me get my mouse here so I can highlight some stuff. Here, what the example is showing is we want to stream data from either a slice, or later you'll see channels, and then we want to specify a function that knows how to, that will receive each element in this particular slice or each element from the channel and apply some kind of operation on top of it, around that particular element. Now, traditional Go, straight Go, there's no way to do that with a group or a simple function that encompasses a logic for multiple types. So what we have to do is declare several functions that takes different types that we're expecting. So here we're using stream int slice, and as it's in the name, you're expected it takes a slice of ints, and it loops over the elements in the stream and apply the function on each element. We see the same thing here with stream string slice. As you would expect, it grabs, the stream is expressed as a slice of string. And it's the same thing here. We loop over the slice, and for each element in the slice, we apply a function. And here we see similar things with a channel. Same sort of thing. We loop over the element from the channel and apply the function. And lastly, string chen, which is a stream of chen of string, and we loop through, or we receive the element from the channel, and then we apply a function. As you can see, it's the same pattern being repeated over and over and over again. When we do that, we get the type safety at compile time, but in order for us to get that, we have to repeat ourselves all over the place. And this is the each function being called and does exactly what you would expect it to do. But here we're going to have to have recourse to to reflection. Now, if you've done any amount of coding in Go, you know that reflection is a powerful tool, but at the same time, you also know that the API for reflection requires a lot of coding to give you the mileage that you're looking for. So here, again, we start with the reflection API to get us some values, and these values have type information and the actual value. So I'm not going to go into reflection here, but you can certainly read about it online. So we have to check what type that's being passed in. If it's a slice or if it's an array, we run the code this way. If it's a channel, we run the code this way. You have to do a lot of type checking because you don't know at build time what your types are. So you have to, make sure that you're receiving what some sort of type that you expected. And when you don't have the type that you expected, you can return an error of some sort. Now, this works perfectly. This is now we have one. We've reduced our code to one function, and it takes different type as far as the streaming is concerned, and the function that applies the operator to each element can work the same way too. It is also kind of a genericized version where now you take an empty interface and you and like I was saying before, you have to apply, because we're using reflection or type assertion. You have to make sure that you checking for types, and so that you don't get in trouble. So although the code is shorter, but now you're having to do more work to make sure that you apply type safety at runtime. And this is basically the same example using one function, and it works. Sorry about that. And it works. So, and here we're using stream with a channel. Okay, so slice and channel works. With this version of the code, it requires you to apply type safety yourself because you're using reflection, and you cannot have, the compiler cannot help you out at this point, and everything is resolved at runtime. All right, so now we're gonna walk through from now on until the end of the presentation. We're just gonna show the true genericized version of the code as proposed by the new generic proposal. So same code. Let me close this. We don't need this. Same code, but now we're gonna start using generic. So stream, we're defining stream as a genericized, as a generic function with a type parameter s. Now, once we declare that we have a type parameter s, we can use that in the proper parameter for the function. And that's what we're doing here. We're saying we take s here, whatever this variable here is, it can use s. And then the function that we're going to apply on each element of s can also take s. And now we see that we have a code that is very similar to the traditional function we saw in the beginning. We're not using reflection. Our type should be resolved for us by the compiler, and we'll see that in a minute. And then here we loop over, because we know that we have a slice. We can use a for range to loop over the slice element and grab them and apply the function and apply the function that we have defined here. And then this is the code being used. So here, we instantiated this function with a type int. And because we said it's a type int, we better have something, a slice of type int. And this is what we have here. We pass it a slice of type int. And now look what happens to our operator function. It also takes a concrete type of type int. And everything now, we're back to using type safety as expected in Go, even though we have a polymorphic function that can take different type parameters. The compiler will be able to help us out with type safety. And it's the same thing here. Instead of an int here, we're using a string, and that's what we're using a string, and the string is specified here. And now we have a slice of string with hello world, and the same thing with the operator function. It now can take a concrete type of string, and we can apply it as we would apply it on the normal code. Just for completeness, I'm gonna go ahead and run this. Let me clear this. So you can see the tool. We see I'm using the go tool, which is a transpiler. It takes the code that uses the proposed version of the generic, that implements the proposed version of the generic proposal, and translate that into current day Go. It's a transpiler. It does what it needs to do to convert what we're telling it into regular Go. Another thing that you have to do is name your type Go2, as we see here, so that the transpiler know that you don't mean regular Go. So let's run the example we just went over, and we have an error. Let's see. I didn't expect the error, so let me Go. Let's debug it. Expected declaration found in one more errors. Okay, let's take a quick look to see what's going on here. And it's on line 9. Sorry. Let's do it again. All right, so now we fixed our comment and it worked. So you see that we're, this is the version that uses a slice of int, and this is a version that uses a slice of string. Once again, I will just show you that we have one function with a type parameter, and that function is able to safely be used with different types. And we've seen that we use it with a slice of string and a slice of int. Now, let's keep going and go to the, let us go to the, to this one, stream 1. And stream 1 is basically the same example as we saw before, but now instead of a slice, we're going to use a channel. So I'm not going to spend too much time here because it's sort of the same thing as we saw with a slice. We have a type parameter here of S, and that type parameter is being used to specify the type for the channel. And same thing here with the operator function that we're going to apply to each element from the string. So the only difference is instead of looping through a slice, we're looping, or we're receiving value from a channel, and then we're applying the function to it. Okay, so you see that it works the same way, and when we call it, it's basically the same way, the same thing. A channel of string here, and then here, stream 2 is a channel of int, but both use the same stream 1, and we get type safety out of it. I think that's pretty cool. And the more I'm learning about what the Go team has been up to with generics, the more I think that it's going to be a big deal once generic lands in the language. Let's keep going and let's look at this version. Let's see what this version is doing. Okay, so this version is using a constraint. Okay, so here's my constraint. I'm calling it StreamItem. It's an interface, and that interface declare that it must have a method called data. All right, and just to be sure, I create a type called StreamItem, and which has as an underlying type a string, and I'm attaching method data on that type. Okay, so now here is the way we use this. The same as before, we declare a type parameter for that function. Once we have a type parameter, well, the type parameter S here now has a constraint. Okay, it's no longer just any type, it's a type that has this constraint, and this constraint means whatever type I specify must have type data implemented, and the rest of it is pretty much the same. For the formal or the traditional parameter list, we have a stream, which is of a channel, and it's of a channel S, and S is being defined here. And again, we have a function of that takes S, which will be applied to each element from the stream. Okay, so from then on, it's basically the same thing. Now, we go here and apply, we loop through, not loop, but we receive each element from the stream and apply the operator function on each element. So it's basically what we've seen earlier. Nothing too fancy, except now whatever type that we apply to, whatever type that we apply to stream must be something that implements data, and StreamItem, as we saw earlier, implements data. Okay, So now we see that we can narrow down our types using constraints. Let's keep going to this version of the code. Check on time here. All right. This version of the code is basically the same, except now I am going to introduce in a constraint called Streamable Item. It's basically the same. It's the same approach, except now I'm even adding more filtering on the type, and the way I'm doing that is using the type list, which is being applied to the interface. So what that means is not only that, whatever type, when I apply this constraint, my type has to support either operations that can be applied on string or bytes, but also it has to support types that have data defined on it. And that's what we're doing here. We define these two types as either a string or a byte, and then we attach data onto those types. So now when I come down here, again, the middle, the implementation of string 3 is what we've seen before. We have a type parameter S. Now it's taking constraint called Streamable Item. We just saw what Streamable Item is. And it does the, excuse me, the very same thing. Loop through, receive the items from the stream, and apply the operator function. Okay, so here the interesting part is now when we're applying, when we're calling our generic type, we can now use string item, and we pass it the item. Our string item has to not only be able to meet the requirement of being a string, but also it has to implement data, which is what string item does. And the rest of the code is basically the same. And here we're doing that with byte items. We're streaming a byte, slice of bytes into this particular channel. And right here, when we get ready to use stream 3, which is a generic function, we have to pass it a type parameter that is instantiated as bytes item. And bytes item meets the requirement, bytes item meets the requirement of the constraint. So now, this particular version of the code does something interesting. It is defining a type, and that type itself has a type parameter. So type chen is I'm defining a type called chen, and I'm saying that type can take type of type t, and I'm using type t as the underlying type for this type channel, for this channel type, right? So here we're gonna say when I define stream type 4, I am saying, hey, look, let's use this type parameter of type t. And this type parameter of type t, we're gonna pass it here to stream, which is a type of chen. Now, the reason why we have to do this is because in order for us, we have to define the type parameter somewhere. So we define it here. And then that type parameter gets applied to chen as t, which is then applied to this guy as whatever the type is going to be. It's going to be the underlying type for chen. And then the rest is basically the same. So let's see how do we, how do we use this? So again, it's the same implementation here. Nothing changed, but the way we use this, stream 4, remember we say we are going to use type parameter of t, and that's what we're using here. So t in this instance is a string. Now string is not only going to be used in the function in the generic function as a type parameter, but it's also going to be used in the generic type of chen as a type parameter. So when I say I want to use string here, that string is also going to be passed here to chen that we define as a type, which also takes a type parameter. So chen here, let's go back down right here. We're saying it's a string, so my capital chen type that was declared above will be of a type chen of channel of string. And once we do that, then it's basically the same thing. We haven't run something in a while, so let me run this really quick. Go to, and then again, we're using the tool command to run go. And this is, let's see, 4. And when we run it, we see that it happily and correctly runs to give us the results that we're expecting. All right, let's see the last one, the last example. I'm running out of time, but hopefully we'll be okay. The last one is I just wanted to show you the complexity that can arise in creating generic code. Like I said, the generic documentation is super long, and as such, you can do a lot of powerful things with generic, but just make sure you read the documentation and understand what you can do, because you can get in a situation where your code does not type at all, does not compile at all. And what I would recommend is start small, create a function or type that takes concrete types first, and then try to use generics around that particular function or type before you start with the generic version first. Okay, so let's see this. So here, what I'm doing is I am declaring a type called a stringable, and I'm applying a type list to it. And then we saw we did that earlier, so it's the same thing. I'm just creating a new constraint. And then let's see, and then I'm creating the same types we had earlier, string item and byte item. And then we have another constraint. And in that constraint, I'm embedding the previous constraint, stringable. Now, because constraints are really interfaces, you can do that. So now streamable item is composed of stringable and what we had before, which is this particular method that must be specified. And then we have the type that we had before. When we define our 5th version of the function, we have to provide a type parameter of t, and it is of streamable item. So it is this guy, which implies that it is also this is going to apply this particular constraint. And then we now can use t in our chen type as we saw earlier, and in our operator function as t. Now, what does that mean? That means the only type that we can use here are types that satisfy this particular constraint. So in the previous version, I was able to use float and int and string, but in this version I cannot, because the only thing I can put in here are types that satisfy these 2 requirements. And I have 2 types here that satisfy those requirements, and basically those are the only types I can use here, or anything that looks like this. And that's what we're doing here. If you look here in the in where it is being applied, stream 5, we're using string item here, and we're using byte item down here. And that is, that is it as far as the demo. And as I said earlier, generic is going to be a very powerful tool once it lands properly in Go. And it's probably going to take the Go team another couple of years to get it right to a place where everybody's happy. Now, even in the document, when you go in and peruse the document and take a look, you'll see that there are tons of corner cases. There are tons of issues that you should be aware of. There are even unresolved issues that the Go team is aware of. And that's why I like that document, because it tries to be as exhaustive as possible in identifying cases where generics may not even work for you. So take a look at the document, give it a read. If you have anything you want to suggest to the team, they read the blog. They talk about how you can reach the team to provide your own suggestion. And then that's it. So I hope you enjoy this presentation. And hopefully, if you have questions, I will take them.
We are live now, so let's check the question. A lot of questions was answered during the talk itself. Let's see what's. So yeah, probably the biggest question, the main question. So Go famously had slow programmers. You have to write all this code yourself. And now we are choosing between slow compilation or either slow runtime. Is it clear what path Go developers are taking right now?
As far as implementation for generics, even when you read the draft, it is clearly stated that there's no assumption being made how it will be implemented. So we should not make any assumption as far as what the speed is, compilation is, or how it will be implemented. But I will say that introducing generics is not going to be, it's not going to be for free. So you will have to have, possibly take a hit at compile time. Again, I cannot say how much of a hit or how little, because even the Go team and the folks who will be doing the implementation, they don't know exactly which way they're going to go with the implementation. So it's hard to say, but definitely when you introduce a feature like generic types and type parameters, the compiler has to do more work to figure out what you mean. So you're definitely going to take possibly some compilation here, but I mean, knowing that the Go designers and the folks working on this, they want it to, they want whatever they're introducing, they want it to still feel like Go. So I'm pretty sure compilation time will be super high on that list of things they want to maintain. So that's all I know. That's all I can, that's all I can speak to.
Yeah, when we talked on the previous conference on Go, we speculated that maybe we can have two modes of iteration, like debug build, which is like for ED, or when you change something quickly, and then the most of the slowdown will be on runtime and some release build. That would be interesting if they go that way.
Yeah, I mean, the thing is, you're making some trade-offs with generics where you're saying, hey, I want my type to be resolved at compile time. So the compiler is going to do a little bit of more work than it does today to figure out what that type will be. But once that type is known, the execution time should be fast, or as fast as it is when you write non-generic code. So that's, I would hope that's what it'll be. So we'll see. And I see there's a lot more. I see code in the
we hardly can take this question live because for it to be recorded, we have to read it. And sorry, maybe we can answer that later in chat. So,
okay.
What do you think? Like, what big changes in Go ecosystem will happen as a result of generic being implemented? Like, for example, I created a somewhat popular Go ORM, object relationship mapping library, and then several different people said to me, "Oh, now you can make this version of with generics," and I'm like, I have no idea. It doesn't look it will be any useful actually. Like, I can't imagine ORM with generics. But what do you think? Maybe some people will web framework with generics.
Right. So it's two part to that answer, right? So just like you, I also have. That's not popular, but I have like a GitHub project that I did back in the day that does data streaming, and it uses interfaces all over the place. And after I've gone through this, I'm thinking, well, maybe I need to see what I would get out of it if I did with generics. I think, you know, anyone who's created tools or who have some sort of framework out there written in Go should go back and look at generics to see if it's something that'll be useful. I wouldn't do generics just to do generics, but definitely go and look to see if generics will bring or make the use of your tool better. One of the things that generics, as you saw in the presentation, when you start using type parameters and parameterized types, it does add to the language itself, and it adds a level of new cognitive gymnastic that you have to do to figure out and for your brain to read the code and make sure that you're reading the code properly, because we're introducing new element to the language. Now, we're also introducing new element to the way we use Go as programmers, so that if I create a package and I put it out, now when you want to use that package and it is genericized with type parameters, that package now has to be used differently. So again, we come back to trade-offs. You know, are you okay with changing the way people use your package, your tool, with new generic elements? Or are you okay with the way it is today, and it may even be simpler to use the way it is today without generic? So that's a trade-off. But again, generic gives you a level of, you know, we assume that generics will give you a level of performance at runtime, because a lot of type inferences that is done, or not type inference, but a lot of the way we write code today with interfaces and empty interfaces, and the way we handle that is with reflection, and reflection can be slow depending on how it is being used and what it is doing. So it's all trade-offs all the way around, even in the use of generics. Now, the other part of the question is, what will change in Go? I think a lot of the built-in packages, a lot of the built-in types, we may see generics be introduced and used and either be rewritten or have additional functionalities that we don't have today. If you know, I had posted on the chat a link to a slew of examples that comes with a dev Go Go2Go branch, and when you read those examples, you can see the directions where the Go team is thinking, because a lot of the like, for instance, there for one thing that come to mind is a set type that's been rewritten with generics. There's a package that adds additional functionality to channels. There's a package that adds additional functionalities to slices, et cetera, et cetera. And all these additional functionalities are made possible because of the new type parameters. So that was a long answer, but hopefully it made sense.
Yeah. So that last part is like something that I personally hope that set type would be very nice, and additional features for slices. Do you think it will end up being in standard libraries, and standard library will have something like container package or something like that with some functions, you know, something like STL in C++?
Yeah, it's possible. I mean, I think if the implementation is backward compatible, doesn't break anything, it's possible. Or it may be that they introduce it in an extra packet, like they've done with other packages, like context, for example, was introduced outside of the standard library first, and then eventually made it switch to the standard library. So we may see something like that where additional types and additional packages are introduced outside of the standard library so that the community can play with it, give it time to bake in and get debugged. And then once we feel that it's completely stable, then it gets migrated in the standard library. So we may see something like that. I have no idea, but it would be nice to have you know, additional types in the standard library. But if not, probably in an external package, but that is supported by the Go team.
Yeah. So speaking of the context, you mentioned that the context package was developed outside initially, then XNet, and then it was just an X and ended up in the standard library. And the way it was added to the standard library is actually through type-ls. So they added type-ls about the same time, and then depending on your Go version, it was the old location of the code used the type-ls from the new Go version, so they are compatible. And when type-ls was introduced, there was a lot of concerns that people will use it everywhere and everything will be so complicated. Do you think that something like that will happen with generics, that people will start using generics everywhere, right? Like every trivial code with generics?
Yes, I do think when generics lands in the code, people will go crazy and start using it all over the place. I mean, it's just like anything else. We saw it happen with channels. In the beginning, people, everything had to be channels. And then eventually we developed traditions around the code and around how to code with channel and without channel, or when to use the sync package and not channels at all. So I think the same thing's going to happen. I think in the beginning, people will go generic crazy with generic types all over the place. And then once we learn how to use that feature, we'll kind of scale back and use it as it is intended. Now, I will say this, and I think I mentioned that on the video, generic is, the proposal is very lengthy, and there's a reason for that, because generic is having to change the language to that extent. I'm pretty sure the implementation of it will be complicated, but the use of generic also can be complicated. I mean, you can you can find yourself creating a package and you're like, oh, I'm going to genericize that package, and you might get yourself in a corner where you creating code that is even more complicated than if you were just to create 2 or 3 versions of that same function, as opposed to creating just one function and then introducing type. Because the whole idea about generic is I'm going to create a function or a type that can work for a number of other types. And when you say that, what you're saying is there's a set of type out there that can work with my generic function. And that's possibly true. But the thing is, the minute you introduce a genericized version of your function, now you have to worry about other things that you were not worrying about before, because now your genericized function has to be able to handle, obviously, when you create a generic function and you give it the proper type, it'll work. But at the same time, you got to make sure that the types that you're taking in and what you're doing with that type works for all the types that your generic version supports. So as such, you're gonna, there's gonna be a level of complexity that if you were to write a single version of that particular code, that you won't have. So generic itself is, it can get complicated. It can get, it can have you create code that may not even work, because if you feed it a specific type, you may have code in there that either that type, that code doesn't support what the type you're feeding it, or or something, or a situation like that. So what I suggest is start with a concrete function with concrete type first, get that working, and then slowly figure out how you can create a generic version of that particular function or that particular type. So that would be my take.
Yeah, maybe you can even write like 2 or 3 the functions 2 or 3
Yes.
times, and
Yes.
only after that. Yeah, and speaking of Go crazy, we talked with Florian on the backstage. He was a speaker there today previously, and we joked that maybe we'll have a linter that will complain, "Hey, you use generics, you shouldn't use generics there," and then Go create a ticket and Jira for tech lead to approve the usage of generics.
Hey, yes, we can dream, right?
Yeah, but yeah, I hope that people will really try it outside of like main big
Yes.
projects, and then yeah.
No, I think, and to like today now, if you're curious about generics, today is the time. Is the start playing with it now, because the Go team has go through extreme effort to give us a tool where we can start playing with generics today. So I would say, follow the instruction, get the build a branch and start playing with it. And at first I would say, before this release of generics, I was like, nah, I was in the camp of I'm okay without generics and I don't see the need for it. But after I played with it, that kind of changed my mind a little bit. I'm like, yeah, I could see where generic would make a difference, especially, like I mentioned earlier, I've written a tool that does where, you can do stream processing. It has data stream coming in and you can write functions as operators. And that particular project is all empty interfaces. And after I've played with generic, and starting to get ready for the stalk, I was like, oh wow, I could see, for people who are clamoring for generics, I see why, because a tool like that would definitely be simpler to implement, because with a generic excuse me, with type parameters, a lot of the reflection code that I have in there, a lot of that would go away. And, definitely be easier to maintain, et cetera, et cetera. But on the flip side, the way that the tool would be used, the way you would use that package would also change. Because today, when you use the package, it's really easy. You just stuff a type in the, like, for instance, just like I had in the demo, you stuff a type in where the empty interface is, and the tool, smartly or intelligently figure out what you mean. But with generics, that goes away. Then now you have to specify your type ahead of time, and you have the whole additional the additional type parameter that you have to specify, et cetera, et cetera. So again, it's a trade-off in both places.
Yeah, I think we just got 2 very good questions in chat. So the first one, how do you unit test generic code? Do you test it with like every specific type, every combination, or just one type?
Well, no. So the answer to that is, the whole thing about generic is that you want to filter down to a set of known type. I mean, that's the whole point about generics, right? Because otherwise, use empty interface, right? Now, as far as testing, sure, you would want to test with, so the code you write, the generic code that you write will have to fit a certain amount of a set of known types anyway, because otherwise it will be a very simple function. But the minute you start putting operators on your type, or you start wanting to call a method on that type, then the list of type that can be used in that genericized version of your function goes down tremendously. So I think at the end of the day, most genericized functions have a set of known type that it can use, and that type is not as wide as, say, for like empty interface. So in a scenario where you're testing, I think you probably should want to run the different types that you think your genericized version of your function will use. And like I said, it's probably not the entire universe of types. It has to be something smaller than what empty interface can support.
Yeah. And yeah, let's take that question from the chat as the last one. Do you think someday interfaces will act only as type constraints? So everything will use generics and will not use interfaces at all?
That's a very interesting question. I would say no. Backward compatibility is number one in what the Go team is doing. So you're always going to have interface that acts as interface does today. And two, just because I have generics does not mean I want what I'm used to be taken away. Interface is very, you could do a lot with interfaces. I mean, the fact that, you can define an interface and then just, the way the interface works in Go is that, you don't have to explicitly say you implement an interface. As long as your type has a set of method on it, then it is implied that you have that, you implement that interface. So I think that particular feature of interfaces is great in a lot of cases. So I don't think I don't think the meaning of interfaces will change. I think what the Go team is saying with type parameters and generic functions, etc., is that interfaces can augment what an interface means. So it's still going to mean what it means today, but when we do have generics, it's going to mean something else. So I think it's just an evolution of what interface is, and I think it's going to mean what it means today, and it's also going to mean what it will mean with generics, if that makes sense.
Yeah, absolutely. I really hope too that interfaces will not go away.
Yeah, no,
we just love them too much.
Yes. Any other good questions?
No. Thank you, Vladimir. That was great. It was our pleasure to have you at the conference, and great talk.
Absolutely. Thank you for the invite. I enjoyed doing the video and I learned a lot about interfaces. Thank you.
Thank you.